So far, we've taken a look in detail at two lifetime distributions, and those are the exponential distribution and the Weibull distribution. This section looks at a new distribution, the gamma distribution, and that distribution has probability density function. F of t is lambda divided by gamma of kappa times lambda t to the kappa minus 1 e to the minus lambda t. Now, as was the case with the Weibull distribution, you have a support t greater than or equal to 0, and you also have lambda as a positive scale parameter, and you have kappa as a positive shape parameter. The cumulative distribution function for the gamma distribution looks like this. Capital F of t is the integral from 0 to t of the probability density function d tau. Now, it's certainly the case that this gamma of kappa can be pulled out front because the integral is with respect to tau, and that's what's done in that second step. Now, at this point, if we make the substitution x is equal to lambda tau, then that will give us this integral right here. You'll recognize the integrand with the e to the minus x and the x raised to the kappa minus 1 power as very close to the gamma function, except the limits are not from 0 to infinity. They are instead from 0 to lambda t. And because of that, this is going to be an incomplete gamma function, and it is the incomplete gamma function evaluated at kappa and lambda t for all t greater than or equal to 0. So that is the cumulative distribution function, and of course if you take 1 minus that quantity, you will get the survivor function because the gamma distribution is a continuous distribution. Well, if the survivor function is messy, you know that you're going to have a messy hazard function, and here is that messy hazard function. One way to distinguish between the gamma and the Weibull distributions is to look at their hazard functions. It turns out that the hazard function for the gamma distribution will approach lambda from infinity when kappa is less than 1, and that is the DFR case. It will be constant for kappa equals 1, and that's the IFR DFR case, which corresponds to the exponential distribution. And then it approaches lambda from 0 for kappa greater than 1, and that is the IFR case. You put those first three bullets together, and you can see that this hazard function will approach lambda for all kappa values, which is to say the limit as t goes to infinity of h of t equals lambda. The intuition behind that limit is that gamma distributions, or gamma random variables, have exponential tails. If the item of interest lasts long enough, then eventually it will look like there are only random failures. That may apply to some items, but not all. Here's a look at the gamma lifetime distribution representations. Let's start this time with the hazard function. Once again, on the horizontal axis you have time as always, and when kappa equals 1, this reduces to the exponential distribution, which has a constant hazard function. When kappa equals 0.5, that is the DFR case. Notice the hazard function now is strictly decreasing. And finally, when kappa equals 2, that is the IFR case. And in this case, you can see that the hazard function is increasing. But in all cases, that hazard function is approaching lambda in the limit. And in this particular setting, lambda has been set to 1 just as we did in the Weibull case. So once again, the hazard function is the distinguishing characteristic, but here are the rest of them. For the probability density function, when kappa equals 1, you get that classic shape for the probability density function. When kappa equals 0.5, you can see a lot of failures early and then it tails out. Kappa equals 2, you get a little bit of a hump shape there, but it's not as bell-shaped as the Weibull distribution probability density function. It's a little bit flatter. Here are the three survivor functions. First one is in the DFR case, then here is the exponential special case, and here is the IFR case. Hazard functions, same thing. Here is the DFR case, exponential case, IFR case. And not surprisingly, because the hazard functions in the limit approach lambda, the mean residual life functions will also approach 1 over lambda, and the three cases given below here are, first of all, the DFR case, then the second is the exponential special case, and finally the IFR case.